Today we're going to be working in section 5.3 on trigonometric graphs, specifically the graphs of sine and cosine. Okay, one thing about the sine and cosine graphs is they have what we call a period of 2 pi. That means that the graphs actually repeat every 2 pi units. So, and that comes because we have the unit circle and we know that it takes 2 pi to get around the unit circle. So every time we go around the unit circle, so we go around one time, and then when we go around the second time, we're going to be hitting all those same values again. And so we end up with an exact replica of the first graph, and therefore the graph has a period of 2 pi, so it repeats every 2 pi units. And we can express that mathematically by saying that t plus 2 pi here inside the sine function is going to be exactly the same as sine of t. So there's no difference in that when we shift it to the left 2 pi units, which is what this effectively does. You're going to end up back at the same place because it has a period of 2 pi. So I want to start out and talk about sketching the graph of the sine function. So if we have the graph of sine, and this should actually be a t, we're doing the graph of one period of y equals sine of t. So if I look at this, we're just going to focus on the sine coordinates for each point. So if I was to be looking at the unit circle, and I'm going to just kind of sketch the unit circle out here. If I was starting here, this point would be the point 1, 0. So the cosine value would be 1 and the sine value would be 0. So that's why here at t equals 0, so at t equals 0, we're going to have a sine value of 0. If we move to pi over 6, which is going to be somewhere in here, pi over 6's coordinates are square root of 3 over 2 and 1/2, and the sine value is 1/2. So we're going to go to pi over 6, 1/2, and then pi over 3, square root of 3 over, sorry, we didn't plot every single one of these. So pi over 3 would be the square root of 3 over 2, pi over 2 would be 1, and so forth. And so when you do that, you end up with a graph that has this shape. This is the shape of the sine function. The sine function always looks like a mountain and then a valley. So it starts at 0, it goes up to 1, it comes back down, goes down to -1, and then ends up back at 0 with that. So it has a period of 2 pi, which means it repeats every 2 pi units. So if we look at a continuation of this graph, this red graph here was that basic graph of the sine function that we looked at for the period from 0 to 2 pi, but that actually continues. So you can see it just keeps repeating. This would keep repeating over and over again. That direction, it goes in the negative direction as well. So you get this wave from it due to its periodic nature.
Okay, I've jumped over to a Desmos screen. Some of you may be familiar with Desmos. We don't use it a lot in our class, but I think it is a good opportunity here for us to just see what's happening. So if I take this, we're going to have our basic unit circle here, and we're going to go up and we're going to look at what happens as we move around the unit circle, plotting the y coordinate of each one of those terminal points. So as I move this value here and go around, you can see that the values are getting more and more. When we get to the top, it's going to turn and come back down again. And if we keep going, at this point, the y coordinate is 0. Here, the y coordinate is -1. And then finally, when we make it all the way back around, okay, so here you should be able to see the ending here. So we'll have this whole part will be one complete cycle of the sine graph.
We could look at the same thing with cosine. With cosine, we're going to be using the x coordinates of each point on the unit circle. So again, if we're talking about the unit circle here and the starting place, we start here at the point 1, 0. So the cosine value for that is 1. So at 0, we're going to be at 1. If we go up here to the point 0, 1, the cosine is 0. So we're back down at 0. Over here, it's negative 1, 0. So the cosine value is negative 1, which is here. And then we go down here to 0, negative 1. So we're going to be back here. And then when we end up around making one complete circle, our cosine is 1 again. So cosine is more like one big valley than the sine function, which is typically the mountain and then the valley as far as how it appears. But one thing to keep in mind is because of the periodic nature and the way that the horizontal shifts can take place, the cosine graph can actually be shifted onto the sine graph and the sine graph shifted onto the cosine graph. So we have to be careful about saying it can only be a cosine graph or it can only be a sine graph, because with the appropriate shift, one could be changed into the other. Okay, so this is just showing the cosine graph, the continuation of it. Typically, when you see cosine graph and sine, you're going to see it graph from 0 to 2 pi. That doesn't mean it stops there. It does continue to go on, but that's just kind of the one period that we typically look at.
Okay, here I've jumped back to Desmos to do a demonstration for cosine. So if we're talking about moving around this unit circle, you can see as we move around the unit circle, this time for cosine, we're going to be plotting the x-coordinate of each of our terminal points around the unit circle, because cosine is the x-coordinate of each of those terminal points. You can see as we start plotting here, we're actually starting from 1 when we do the plotting. Okay, when we get up here to the top of the graph, the top of the unit circle, we're going to be at 0 on the actual graph itself. When we move on around to pi on the unit circle, then you can see our x-coordinate would be negative 1. If we move on around to 3 pi over 2, then the x-coordinate is going to be 0 again. And if we move back around to 2 pi, the x-coordinate is going to be 1 again. So we end up where we started because of the periodic nature of the function.
Okay, the sine graph, if you notice here, we've talked in the last section about the fact that sine is an odd function. And in relation to how odd functions are graphed, odd functions are symmetric with respect to the origin. So when something's symmetric with respect to the origin, it's basically like a pinwheel. If I pinned this here and I spun it 180 degrees or halfway around, it would end up back on top of itself if it has symmetry about the origin. Cosine is an even function, and an even function, it has symmetry with respect to the y-axis. So if I folded this here on the y-axis, this part is going to fold over on top of this part. So it would have symmetry about the y-axis for cosine. So sine is an odd function, cosine is an even function.
Okay, I'm back to Desmos for a demonstration on some of the different translations that we can do with our sine and cosine graphs. Typically, I do this as an activity in the class, but because we're not in class, I'm just going to demonstrate some of this for you. If we look at this, we're talking here about sine. We're putting an a in front of it. So if I look at when a is 1, which is just our basic standard graph, may not be able to get it exactly 1 here. There we go. Okay, so you can see it starts at 0, it goes up to 1, it comes back down to 0, and it makes one complete cycle. Here 2 pi is 6.28, so that's why we see it over here at 6. So here's our one cycle of the sine function. And on this, it goes up to 1 and down to negative 1. So I want you to watch what happens as we change the a here. So as we change the a, it's going to get larger and larger. It's going to get stretched more and more vertically. And that goes back to what we said about when we put a number in front of the function, it's going to be a vertical stretch for that. This particular type of vertical stretch is called its amplitude. So it's a special term for trig functions. So the vertical stretch is going to be represented by the amplitude, and it's always the absolute value of that. So a smaller amplitude, you can see it's not going to be stretched as much. A larger amplitude is going to be stretched further. Okay, so here's one where we're going to look at if we have a negative a. Based on what we know about translations, a negative a is going to actually reflected in the x-axis. So I'm going to take this back to our standard graph, which starts at a equals 1. It's a little hard to manipulate here. So at a equals 1, we start with our standard sine graph. And if I go in the negative direction, you can see that it reflects it. And the larger this a is in the negative direction, then it keeps stretching it in that direction. If I go in the positive direction, then you can see it stretches it in the positive direction. So you can kind of see what happens when you go from a positive amplitude and then the negative in front of it's going to reflect it there. Right here, if we have a plus D out or any letter, but basically we're adding something to it, then this would be like our vertical translation, so vertical shifts. So you can see here we have what we call a midline. The midline here is at 0. So if we move that, if our D is positive, then we can see that our graph is going to shift up. If our D is negative, our graph's going to shift down. Okay, so it just slides it up and down based on the D that we have for this. Okay, if we have something inside the parenthesis, then based on our translations before, this is going to move it left or right. And so here you can see if we start with C is 0, then our sine graph is starting here at 0 as we would expect. And as C increases, you can see that it actually shifts, but typically what happens is we're just going to show the graph here around the origin. So as it shifts, you can see it kind of sliding to the right. But due to the periodic nature, at some point it starts to look like a wave, but it is still sliding to the right. But if it slides far enough to the right, then it just ends up back on top of itself. Okay, so this one we can actually go, if it with a plus, we're going to be moving this to the left, and you can see that that's what's happening here as it moves to the left. Okay, this is one that I particularly want to talk about. When you have a number in front of the x here between the sign and the x itself, what happens is that affects the horizontal stretch and shrink of the graph. So when it's inside here, then we're going to see that that tells me how many sine graphs I can have between 0 and 2 pi. So typically it's sine of x, so I would have B would be 1, and I would have one sine graph between 0 and 2 pi. But if I change B to 2, okay, so let's start here with B equals 1. When B equals 1, I've got one sine graph between 0 and 2 pi. So 2 pi is over here where this dot is. Okay, if I want to change that now to 2, okay, so when I go to B equals 2, I can see I've got one cycle and then I've got another cycle. So I've got 2 complete cycles between 0 and 2 pi. If I change my B to 3, then here I've got 3 complete cycles between 0 and 2 pi. Again, remember 2 pi is 6.28, so that's this point here. And that was supposed to have been at 3. Okay. If I go to 4, then I get 4 complete graphs between 0 and 2 pi, and so forth. So if I go all the way out to, let's say, 10, if B is 10, then if I look at between 0 and 2 pi over here, I've got 10 complete cycles of the sine function in there. Okay. All right, we can also look at it when B is less than 1. So I'm going to move this over to where B is 1. So we're starting here with our standard sine graph. But when B is less than 1, if you notice what happens here is it actually stretches it out. Okay, so let's look at B being 1/2 or 0.5. So what happens is here is my 2 pi or 6.28 is going to be measured here. So I only see half of the graph shown. And that's what I would expect because the B tells me how many sine graphs I see between 0 and 2 pi. So if B is 1/2, then I only see half of a sine graph. If b happened to be 0.2, then I'm going to only see 2/10 of a sine graph and so forth. So the closer I get to 1, the more of the complete graph I'm going to see.
Okay, if we look at these different transformations, the first one here, we've got f of x equals 2 plus cosine of x. So anytime something is added out either in front or behind, this is going to be a vertical shift. So this is actually going to slide the cosine graph up 2 units. So if we look at the graph for this one, our basic cosine graph starts at 1 and has a period of 2 pi. So it kind of goes from here to here, even though it's showing more a continuation of that. So the plus 2 means it's going to take each one of these points and slide it up 2 units. So you can see how the blue graph is going to slide up to be the red graph. So everything slides up for the vertical shift. Okay, if you have a negative in front of it, this goes back to those same rules we've looked at before. This would be a reflection in the x-axis when we have a negative in front of the function. So here cosine again is the blue graph, and if we reflect that in the x-axis, it's going to reflect down and become the red graph. Okay, we can also put a number in front of the function, and that's actually going to have the same effect that putting a number in front of any function does, and that is it's either going to vertically stretch it or vertically shrink it. So if the number in front is less than 1, so if our a is less than 1, then that's going to be a vertical shrink. And if a is greater than 1, it's going to be a vertical stretch. Okay, so on this one, if you look at this graph here, my basic sine function, my basic sine graph is the blue graph here. So if I go and I put a 2 in front of it, then this one's going to be a vertical stretch. And you can see that that's the red graph here. So it doesn't change our intercepts. Our intercepts stay the same. It's just kind of like a rubber band that's getting pulled up. So instead of going up to 1, it's going to go up to 2. Instead of going down to -1, it's going to go down to -2. Here, if you look at the one with the 1/2, the 1/2 is going to be a vertical shrink. So instead of going all the way up to 1, it's only going to go up to 1/2. So it's going to be a little bit flatter and have less amplitude. We'll talk about amplitude in just a minute. Okay, so the amplitude is the absolute value of this number here in front. So whatever the vertical stretch is, it's the absolute value of that. So amplitude is never going to be negative. So if you're asked to report your amplitude or to give that as an answer, it always needs to be a positive answer. So the amplitude is the largest value that the function attains in this. It's basically the distance from that center line up to its maximum point. So it's this distance in here. Okay, and that vertical line may be shifted, but it's the distance from the vertical line. Sorry, I'm saying vertical line. From the horizontal line, that center horizontal line, from that center horizontal line up to the top or down to the bottom, whatever that distance is, that is your amplitude. Okay, so on this one, you're asked to find the amplitude of this function. So this is my A, so the absolute value of that is going to be my amplitude. So the absolute value of -3 would be 3. So we'd have an amplitude of 3. As far as sketching the graph goes, you start out with your basic cosine graph, which you see here in blue. And we've got a couple things going on. One is we have a vertical stretch, so we're going to stretch it from 1 to 3. So instead of starting here, we're going to start up here. We're going to go down to -3, go back up, and then we're going to reflect that in the x-axis, and we're going to end up with this nice red graph that's drawn in for us here. Okay, we can also have changes in the period. So we have the standard period that's 2 pi. But anytime we have a value here that's in front of this x that's not 1, then we're going to have a period change. Okay, so 1 period, like I said, is going to typically be from 0 to 2 pi, but we can change that, and actually if we have a k in front of this or some number in front of it, the effect on it is going to be that it divides the period 2 pi by k. And I have this summarized on another slide a little bit better, so I'll show you that in just a minute. But what this number is, this is the number of complete cycles between 0 and 2 pi. Okay, so if I had the number 3 here, then that would say, I would expect to see 3 complete sine graphs between 0 and 2 pi. So what's happened is that has had to like smash them together. It's actually compressed them of like a horizontal compression or horizontal shrink, basically, with that. Okay, so the period of sine and cosine we find by doing 2 pi over k, where k is this number in front of the x. Tangent we'll talk about next class, but that is pi over k, so that's a little bit different. And then, like I said, k is the number of complete cycles between 0 and 2 pi. And I think as we go through some examples, this will make more sense. Okay, so on this first one here, we've got the sine of 2x. So this is my k here. K is going to be 2. So the period is 2 pi over k, or 2 pi over 2, which is pi. So what that tells me, if the period is pi, then I go over here to pi. So between 0 and pi, I'm going to see 1 complete sine graph. So it's going to leave and end up back at the same place. Okay, so it started at 0, ended up at 0, and it had 1 complete cycle there. So that's what my period tells me. The k tells me that if I look from 0 to 2 pi, which is here, tells me how many sine graphs I'm going to see. So I'm going to see 1 sine graph and then 1 more sine graph. So I see 2 sine graphs between 0 and 2 pi. So the k and the p tell me something related but still different. Here the k is 1/2. So what that's telling me is I expect to see half of a sine graph between 0 and 2 pi. So here's 0 and here's 2 pi. I'm only seeing the mountain part of sine. I'm not seeing the mountain and the valley. So that would be half of the sine graph that I'm seeing there. So the period for this is 2 pi over that k. So 2 pi over 1/2. So that's going to be 2 pi times 2 over 1, or 4 pi. So the period is 4 pi. So that means in order to see an entire sine graph, I have to look at 0 all the way out to 4 pi. So if I'm looking from 0 to 4 pi, then I see 1 complete sine graph. So what these are doing is these are horizontal shrinks and horizontal stretches. So if it's less than 1, it's a horizontal stretch. If it's greater than 1, it's a horizontal shrink. And so this is kind of summarizing this. You can see that on this one, the period is 2 pi over 2, which is pi. So we see 1 complete sine graph from 0 to pi. This one we just got through doing, so 2 pi over 1/2 is actually 4 pi. So if I look at this, the blue graph, I see 1 complete graph from 0 to 4 pi. And here, if I do 2 pi over 1/3, I'm going to get 6 pi. So it takes me all the way out to 6 pi before I get to see one whole sine graph that's being shown. The good news is cosine works identical, so we don't really have to differentiate between the two. If I look at this first one here, my amplitude, which is the first thing it's asking me to find, my amplitude is the absolute value of 4, so that's just going to be 4. The k in this one is 3. So the period is going to be 2 pi over k, or 2 pi over 3. So if I go to sketch this, I'm not going to ask that you do a lot of sketching by hand because you have your calculator. But basically the period is 2 pi over 3. So if I come over here to 2 pi over 3, then I need to show a complete cosine graph between 0 and 2 pi over 3. Okay, so this is the graph that I have shown here. Okay, if I look at the next one, this one I have an amplitude is going to be 2 because it's the absolute value of this number. The k is 1/2, and the period is 2 pi over k, which gives me 4 pi. Okay, and I thought I had a graph of that, but apparently I don't. But basically what we're going to do with that one is I'm going to go from 0 to 4 pi. So I usually like to mark this off in fourths. So this would be 2 pi, pi, and 3 pi. And it's going to be stretched by 2 and reflected. So my basic sine graph is going to go up to 1. So it's going to look like this. And then if I stretch it, it's going to go up to 2 and down to -2. And then if I do the negative in front of it, that's going to reflect it. So instead of going up to 2, it's going to go down to -2 and up to 2. And so this last one that I did, that's my final graph, and that's the one that should represent -2 times the sine, or -2 sine of 1/2 x. Okay, we can have what's called a phase shift, which is basically our horizontal shifts. The horizontal shifts, just like before, are within this parenthesis. So just before, we would have something that looked like this. This would represent a horizontal shift. That's going to be the same when we have these trig functions. If it's inside the parentheses, it's going to represent a horizontal shift with that. So if we look at some of these examples here, this one we've got to find the amplitude period and the horizontal shift, also called the phase shift for this particular trig function, and then graph one complete period. So if we look at this, we've got, this is our amplitude is 3, our k is this number here, so that's going to be 2. And this is going to give me the phase shift or the horizontal shift, so it's going to be going right pi over 4, or it might just be identified as plus pi over 4. So the period is 2 pi over k, so k is 2, so we end up with a period of pi. So if I look at the graph here, I have a period of 0 to pi. So what I typically do is divide this into 4 parts. Okay. All right, so we want an amplitude of 3, so that means it's going to be stretched by 3, and we're doing the sine graph, so it's going to look something like, see if I can do this a little bit better here, something like this. It should be curved and smooth. All right, so we have this, that takes care of the change in the period, and it takes care of the amplitude. Now the horizontal shift, that's going to be your last thing you do. So we're going to move it right pi over 4. So this point is going to shift here. This point shifts here. This one shifts here, here, and then here. So you end up with a graph that looks, depending on how smoothly you can draw it, it looks something like this and goes all the way out to 5 pi over 4. Just remember that this does continue going back this way, and it keeps going this way as well. So the periodicity of it allows it to keep waving and keep going there. Okay, so this is just a better graph. You can see that we originally had a period of 0 to pi. We shifted it to the right pi over 4, and we ended up with this graph here. So what we can do to find one complete period is actually take the interval that we started with, which was 0 to pi, and just add the phase shift to that. So if we add pi over 4 to each one of our coordinates here, instead of showing it from 0 to pi, we're going to be from pi over 4 to 5 pi over 4, that we want to show one complete period. Okay, here's another one. This one has a little different twist to it in that the K is actually inside the parenthesis. So before we can identify the different things that we need to identify, we've got to actually factor this K out. So whatever's in front of the X, we're going to factor that out. Okay, if we factor out a 2 from the 2/3, that's going to be this 2 comes out. So I'm going to be left with just the pi over 3. Factoring is division, so basically we're going to say 2/3 divided by 2. So 2/3 times 1/2, and that gives me 1/3, and that's what we see here. So once you get it to this point, you can pretty clearly identify what you need. Your amplitude is going to be 3/4. The K is 2, so the period is 2 pi over K, which is just pi. And then we're going to have a horizontal shift left pi over 3, or you may see it as negative pi over 3. And this is what the graph would look like. So our cosine graph, we know typically would start at 1, but this one, because of the amplitude change, it's going to go up to 3/4, but it's actually going to be shifted left pi over 3. And so that's where we end up with this point being back here. And then we have the cosine graph that's drawn in. Okay, here's one for you to try. So try this one, identify the different values for this, and then we'll take a look at your answers. Okay, the 3 is the amplitude. This is the K, so we would expect to see 4 sine graphs between 0 and 2 pi. This is the phase shift, so I'm going to be going left pi over 3, which will be negative pi over 3. And this is going to be the vertical shift. It's going to be up 2. Okay, here's another one for you to try. So take a minute and try this one. Okay, the first thing on this one we need to do is to factor out the 4. So we're going to have y equals 3 sine of 4, and then x plus pi over 3 plus 2. So my amplitude is the 3. The K is 4. My phase shift or horizontal shift is going to be left pi over 3 or negative pi over 3. And then this is going to be up 2. Okay, sometimes we just really need to use our calculators to graph these because trig functions can get very complicated, especially if the periods have changed. So I'm going to show you a graph or two where you really have to be able to find the appropriate window for viewing it. If you look at this particular graph here on different windows, what you're going to see is, if you look at the window from negative 12 to 12, then you look like you have basically just your original graph here, your original sine function. If you look at it from negative 10 to 10, then you see a lot of oscillation in here with that. And then here you can see negative 9 to 9, you can see a very different interval. And then again from negative 6 to 6. So there's lots of different viewing rectangles that make the same function look very different. And that's one reason identifying the period is very important, because here, this is our K. So the period is 2 pi over 50, which is pi over 25. So that basically means we see one complete period of the sine function between 0 and 1 and 0.126. So there are quite a few sine functions pressed into the interval from 0 to 2 pi, and that's why we see all the oscillations that we do. So one last function here that I wanted us to look at, and that is this function sine of x over x. Again, a lot of times graphing these on your graphing calculator is important because you can kind of see what the function is doing. This particular function, if we were to plug 0 into it, we would have the sine of 0 over 0, and that would be an undefined expression. So when we start working with calculus a little bit later, whether if you go on to calculus, then you're going to be looking at taking limits. And so what's important sometimes is not what it does at that point, but what it's doing close to that point. So getting your correct window to look at these graphs is really important. So sometimes you just have to play around with them a little bit and figure out the window that is going to be most appropriate for what you're looking for. So here, if we're looking to see what the graph is doing near 0, you can see that even though it's undefined at 0, it actually gets closer and closer to the value of 1 on that. Okay, so here's one last example if you would like to practice with this. Okay, so here would be your amplitude. Your period would be 2 pi over k, so 2 pi over 3. This would be right pi over 2, and then up 1 for that. And this is just kind of going through those different steps. You've got your basic sine function. If you have a 3 here, then that means we're going to see 3 graphs from 0 to 2 pi. So this is 2 pi that we're seeing. Here it's going to stretch it by 2, so that's the red graph. Here we're going to take everything and shift it up 1. So when I do that, that's this blue graph that goes up to the top. And then here we're going to shift it to the right pi over 2. So if we're going to take the blue graph and shift it right pi over 2, we're going to end up here where the green graph is. So on this particular one, the period was 2 pi over 3, and we have a phase shift of pi over 2. So that's why this graph is shifted almost on top of itself, because pi over 2 is not that much less than 2 pi over 3. So if it were shifted just a little bit more, then it's going to end up right on top of itself here. And so this is just the final graph for this one. So I wanted to look at a couple problems here that are very similar to some of your homework, just to help you be able to understand your homework a little bit better. So this one, it's actually showing you a graph and asking you to take the information from the graph here. So if I look at this graph, this has the shape of the sine function. Okay, because we start at 0 and we have our mountain and our valley. Our amplitude we can find from, we look at this center line across here, and we want to see how, like, the difference between the peak and the center line. So that has a difference of 5. So that's going to be my amplitude. The period is how far it takes to complete one cycle. So from 0 to 2 pi. So the period on this one would be 2 pi. And there is no horizontal shift on this one, so that's going to be 0, because normally the sine function starts here at the origin and our graph is starting at the origin. So if I put this all together and write my equation, I'm going to put my amplitude, and then I'm going to have sine. If it is, to find the k, we know that the period is 2 pi over k. So if I solve this equation, just cross multiply, then what I have is k is 2 pi over the period. So the period here was 2 pi, so that's going to be 2 pi over 2 pi, or just 1. So k is going to be 1 in this case, and I have no horizontal shift, so my equation is just y equals 5 sine of x. Okay, on the next one, this looks like a cosine graph because it's starting away from the origin up here. So here's my center line, and if I look at that center line, the difference here between the maximum and that center is 5/2, and that's going to be my amplitude. The period on this one's a little bit harder to identify. If you look at this in terms of fractions, this would be 1/6 pi. So here is going to be 2/6 pi. This is going to be 3/6 pi. And then over here is going to be 4/6 pi. Of course, some of these fractions will reduce. This one would be 1/3 pi, 1/2 pi, and 2/3 pi. So what I'm showing you here is that the whole period for this particular graph is going to actually be 4 pi over 6, which is the same thing as 2 pi over 3. We have no horizontal shift because typically for cosine, it starts at its peak here on the y-axis. So that's going to be 0. So when I put this together, I'm going to have y equals 5/2 times the cosine. The k, if you remember, we just got through looking at k is 2 pi over the period. So that's going to be 2 pi divided by 2 pi over 3. So if I do keep, change, flip, then my k is going to be 3. And there is no horizontal shift, so I'm just going to have an x. So this is my equation here. The next one, this one, if I look at it, it has an amplitude of 7 because that's how far we are off this center line is 7 units. The period is going to go from beginning to end. This is 1/2 unit, another 1/2, and then another 1/2. So what we've got is 3/2 or 1.5 for the period. The horizontal shift on this one, we're going in the, we're shifting it where it would normally have started here. We're actually shifting it back to the left. So we're going to have a horizontal shift of -1/2. And then for the equation itself, it's going to be y equals, our amplitude was 7 times the sine. The k is 2 pi over the period. So 2 pi over 3/2. Do keep, change, flip. That's going to be 4 pi over 3. And then we just said that we're going to shift it left 1/2. So to have a shift to the left, this is actually going to need to be a positive, and that's going to be our equation. Okay, if we look at this one we're going to model with the sine function as well. So our amplitude on this, we go up to 7 and down to -7, so we have another amplitude of 7. The period, if we look at how far we are from beginning to end, then this is 3/4 units plus another 1/4. So 3/4 plus 1/4 gives us 1 for the period. And the horizontal shift, this one we would have normally been starting our sine graph over here. So we're basically taking and shifting this to the left 3/4. So our horizontal shift is going to be -3/4. So I need to figure out what the k is going to be. So k is 2 pi over the period. So 2 pi over 1 gives me 2 pi for the k. So my equation is y equals 7 sine 2 pi x plus 3/4. The transformations of our sine and cosine functions. Next class, we're going to be looking at the graphs for tangent, cotangent, secant, and cosecant. And so we need to really master sine and cosine first because those are your primary graphs. So be sure that you understand the characteristics and how to get all of the period, amplitude, phase shifts, and so forth. Okay, thank you and have a good day.